Hi everyone, I'm Bill Stewart. I work at Microchip's Automotive Products Group. I would like to introduce you to Microchip's CryptoAutomotive in-vehicle networking development kit. This kit emulates both the Trust Anchor and the boarding security device from Microchip. Final silicon will shrink the security capabilities of the kit into the compact form factor of a 5x5 QFN. Both automotive devices will allow a customer to add comprehensive security to network vehicle systems. And because these products are companion HSM devices, there could be minimal impact to integrate one of these secure elements into a customer's current design while still providing the highest level of protection against threats. This means a customer might be able to keep their current 8, 16, or 32-bit device already designed into their ECU. We have created a demo with the development kits to showcase one of the many features of the security devices, which is secure communication. The demo has 3 ECUs. The first is an off-the-shelf automotive cluster connected to one development kit. The second is an industry-standard CAN/CAN-FD tool provided by K2L. The CAN tool is the optimizer Mocha FD, and this is connected to another development kit. And the third node, which we call the intruder node, represents an ECU on the CAN-FD bus that has been compromised. Prior to this video, I have provisioned the kits to share the same symmetric keys that will be used for secure CAN communication. This demo uses CAN message authentication codes, or CAN MACs, to achieve this. The CAN MAC allows the receiver to confirm the message came from the expected sender. The CAN tool transmits all the messages to put the cluster into a normal runtime state. All of those messages are going through the development kit connected to the tool. Using the kit's development GUI, I have configured 2 of the messages to have CAN MACs. In the kit tied to the CAN tool, the messages will get the CAN MACs appended. And in the kit tied to the cluster, the messages with CAN MACs will get verified. And if the MAC is valid, the payload is passed up to the cluster. All other messages are considered to be passed through to the development kit. The CAN tool is monitoring traffic between itself and its respective kit, as well as traffic from the CAN-FD bus, which we consider the vehicle bus. When I initially power up the demo, the cluster behavior is in a stable state. You can also notice the cluster is on and the speed is set to 60 miles per hour. Note that we have not enabled secure communication at this time. This is noticeable in the messaging showing up in the trace window of the CAN tool GUI. The CAN frame from the tool is not modified by the kit, so the payload contains no CAN MAC. At this point, I am able to transmit a successful spoof attack from the intruder node. This attack is spoofing the speedo message. Notice the cluster speed needle appears to be in contention. This is because the cluster is receiving a valid frame from the CAN tool, attempting to set the speed to 60 miles per hour, while the intruder node is also sending a valid frame to the cluster, directing the speed to be different. Depending on what the speed the intruder attempts to send to the cluster, the attack might not be noticeable on the cluster. But the attack would be obvious when looking at the messaging on the bus. Now when I enable secure communication, you can notice that the cluster now displays 60 miles per hour. We can look at the trace window to see why. The speed message on the CAN-FD bus contains additional data appended. This additional data contains the sequence or freshness counter and the CAN MAC, which was calculated over that message. And recall, the kit tied to the automotive cluster will receive and verify that MAC. And if it is valid, the kit will pass that data up to the cluster. Notice the attack is still ongoing. If it is invalid, the message is thrown out and the area event is stored. The security device can then notify the host micro in order for it to react. Let's look at another spoof attack. Again, we will disable security, and then enable the second spoof message attack. This time, we will spoof the ignition message. This attack will be visually noticeable by the driver. And as before, enabling security corrects the situation and puts the cluster back into a stable runtime state. Thank you for your time. I hope this demonstration was helpful. If you're interested in understanding more about how Microchip technology can support your automotive security needs, please reach out to us through your local sales office.